No one wants to beat it. Show I'm even strong as your fighter. It doesn't matter who's from the break. Just beat it, beat it, beat it, beat it. Beat it, beat it, beat it.
Howdy y'all, my name is Casey Cohen. I will be talking about the structures and RECO portions of this vehicle. So you can kind of see the vehicle here in CAD. It's not too complex. We have our standard carbon fiber laminate fins, carbon fiber body tubes, interstage coupler, and then our fiberglass nose cone. We will also have a short section of fiberglass on this upper tube here, but it'll be in conjunction with the carbon fiber tube, so it'll be seamless. And so yeah, we do plan on using flyaway rail guides on this that we have flown and tested on a different vehicle. So we're confident in not having to use 1515 rail buttons on the booster here. So we are running from a K350 to a J99, attempting to coast for approximately 7 seconds. This will leave us with an altitude roughly around 28,000 feet. And if we do end up hot staging, which we are comfortable with, we will be around 25,000 feet. Here you can see one of the cross sections of our sustainer. So there's nothing too complex here. We will have a little forward retention for our casing, and then we'll have a very similar bulkhead put in place for the RECO shock cord here. And then you can kind of see the insides of our avionics bay here. We're just doing kind of standard head-in deploy and then jar gun here. And then we'll just use some 1/4-inch aluminum tubing for our charge cannons. That way we're comfortable deploying at 28,000 feet without any risk of a snuffed charge. So nothing too complex going on with the avionics sled itself. Two sets of micro screw switches. One will be for the Blue Raven and one will be for the Featherweight GPS. The other will be shunting our ignition wiring until we are everything armed upright on the pad and ready to walk away. You can see our fins are slotted right here, so they will go over our interstage coupler, and the coupler locks into the top of that tab right there. And so it should provide that rotation locking that we want, as well as allowing us to grab over the body tube and casing thrust ring. So we're not worried about any kind of issues with our fins or having a weirdly slotted interstage coupler. Here is a cross section of our booster section of the vehicle. It's a little less complicated. We are just doing single deployed apogee here. We'll still be using the charge cannons just for simplicity's sake. They're easy to use. You can see a bit of our interstage coupler here, and so we'll be using a molybdenum disulfide lubricant on that as well to help us drag separate, because we will not be using a staging charge for this vehicle. That's kind of just a decision just in case we don't want to accidentally put any oscillations into our sustainer, as well as we believe we can drag separate. In worst case, we just hot stage and still perform pretty well.
Howdy everyone, I'm Akash and I'll be presenting on the dynamics and performance of the vehicle. Starting off with, the rocket is about 87 inches long and has a diameter of 54 millimeters, making it a minimum diameter rocket. It has a total wet weight of about 12.6 pounds, of which 5.5 pounds are in the sustainer. The first step in the design of the vehicle was the selection of the motors. This was a complicated optimization problem, trying to maximize the score, which required both maximizing the altitude while making the impulse as close to a full K as possible, subject to constraints of maintaining off-the-rail velocity and other factors. In order to evaluate this, we designed a model rocket and selected different motor combinations in order to fly in it. Based on these performances, we selected the Loki K350 and the Aerotech J99 as our motors of choice. Both these motors have relatively long burn times and low thrusts for motors of their category, which enables very high performance because of their long burn times. However, they still have sufficient thrust in order to hit our performance requirements, such as off-the-rail velocity and consistent acceleration throughout the flight. With the motors selected and the overall length of the body tubes and nose cone size based on other factors, such as what has to fit inside of them from a recovery and golf ball perspective, the next step was the design of the air surfaces of the vehicle, namely the fins. Here, the sustainer fin design is presented. There are two notable characteristics of this fin. First, part of the root core is cut out, as you can see at the bottom, in order to fit our interstage coupler. This reduces the overall rigidity of the fin, making it more vulnerable to aeroelastic flutter, but because of the relatively low Mach number that this vehicle will be flying at, we evaluated that this would not be a significant concern. The second characteristic of its fins is its relatively low span of 1.75 inches, which is less than the rule of thumb of one caliber. Because we expect because these are sustainer fins and we expect little angle of attack to be seen on the sustainer, we don't think that blanking is a significant concern, so we're okay with less than one caliber fins. Overall, these fins were optimized for high performance while ensuring sufficient stability for the flight. Here are the booster fins. They were similarly designed to maximize performance while ensuring stability of the vehicle. They have the same characteristics as the previous fins, with the exception of the fin span, which has been increased from 1.75 inches to 2.3 inches. Aeroelastic flutter is a significant concern for these types of vehicles, given their thin fins and relatively high Mach numbers compared to other hobbyist rockets. In order to avoid failure modes like these, we evaluated the fin performance using FinSim, with the material properties isolated there, as the fins are made out of a carbon fiber laminate. Using the conservative 2D lift curve slope model in FinSim, we found the following Mach numbers that the fins were expected to fail at. Given the max Mach number of the rocket is about 1.01, we see that there are significant factors of safety for all failure modes. Furthermore, we know that the 2D lift curve slope model is very conservative, and so we expect higher factors of safety in actuality during the flight, even given the strange geometry of the fins. With the aero surfaces and overall configuration of the vehicle determined, the next step was optimizing the number of golf balls that we fly. We conducted a sensitivity analysis where we minimally modified the rocket in order to support configurations from 10 to 15 golf balls, and we have a plot of the results below. You can see that the sensitivity analysis shows that 12 golf balls is approximately optimal, although when worse conditions were evaluated, 13 to 14 golf balls became slightly preferable. Based on the conditions we expect and the robustness of the rocket to worse wind conditions, we expect that 12 golf balls would be optimal for the actual cup itself, and so we're selecting 12 golf balls. These considerations lead to this overall final vehicle consideration, the same as presented before. We start with a carbon nose cone with a length of 9 inches, corresponding to an aspect ratio of 4 to 1, the parachutes and such, which we'll discuss later, and the fins that are detailed before. The overall performance of the rocket is presented here. You can see on the right that the Mach number is just about 1 for both the booster and sustainer burns. Based on this Mach number, we picked Open Rocket as the simulation tool of choice because its results were basically the same as RAS Aero for these low Mach number regimes. You can see that the overall performance altitude of the vehicle is about 28,000 feet. Here we see the stability of the rocket. You can see that it's consistently over 2 for the entirety of the flight, meaning that it's a stable rocket that's likely to fly straight even in high wind conditions, and is likely to have a long time before the rocket tips over after booster burnout, ensuring the sustainer motor will be able to light after an extended period of time. In addition to just evaluating calibers, we also evaluated stability in terms of percent stability, which is important for the very high aspect ratio rockets that you see for the full stack configuration between the booster and the sustainer. Based on all the criteria that we evaluated, we see this rocket is particularly stable and is likely to fly well. Here's a summary of the overall performance of the vehicle. You can see that in best case scenarios where there's little winds and the rocket is flying straight up with a long time between booster burnout and sustainer burn, we reach an altitude of about 28,500 feet, all the way to 25,700 feet in the worst case scenario of high winds and low time between booster burnout and sustainer burn. That corresponds to a score between 90,000 and 100,000.